Welcome to Math Shorts, tantalizing mathematical tidbits that will amaze, entertain, and delight. Math Shorts is brought to you by the Ottawa Zone for Mathematics Education. The Ottawa Zone for Mathematics Education is a chapter of the Ontario Association for Mathematics Education. Information about both organizations can be found in the information for this video. In this episode of Math Shorts, we're going to be looking at factorials. And to get an idea of what factorials are, let's start with a problem. Three friends, Lenny, Sophie, and Srin, want to take a group photo. How many different ways can the three friends line up for the picture? So take a second, pause the video, and see if you can answer this. And look for any patterns. See if you can discover what we're going to be looking at in this video. So the numbers are small enough, we're only dealing with three people, that we can actually just go and list all of these possible things out. So we could actually have Lenny, Sophie, then Srin. Or we could have Lenny, Srin, then Sophie. We could have Sophie, Lenny, then Srin. We could have Sophie, Srin, then Lenny. We could have Srin, Lenny, then Sophie. And finally, we could have Srin, Sophie, then Lenny. So that gives us a total of 6 possible ways that these friends can line up for the picture. But is there a way that we can sort of analyze this mathematically? Is there a pattern that we don't have to write out all of these different arrangements of the friends? So let's look at this a little bit more carefully. So if I'm lining three people up for a picture, first thing I got to do is pick the first person in the line. And I've got 3 different ways that I can do that. Either Lenny could be first, or Sophie could be first, or Srin could be first. Now for each of those choices, I'm going to have 2 possible choices for the next person, because I've already used up one of my 3 people. So for example, for Lenny, we could either have Sophie or Srin next. Similarly, there's 2 choices for Sophie for the next person, and 2 choices for Srin for the next person. Now, once we've got 2 people lined up, there's only one other person to go. So the only choice for the last one is the last remaining person. Now if we look at this, for each of these 3 people, I've got 2 possible choices. So the total number of choices for first and second is 3 times 2. And same thing for the last one. We've only got 1 choice here, so it's going to be multiplied by 1. So if I look at the total number of choices, it's going to be 3 times 2 times 1, which gives us 6, which was the total that we found at the beginning. Now, this product, or products like this, 3 times 2 times 1, where we're multiplying a bunch of consecutive integers together, shows up all the time in mathematics. As a result, mathematicians have a notation for it. So they write it as 3 with an exclamation mark after it, which means all of the numbers from 3 down to 1 multiplied together. And we read this as 3 factorial. Now, we don't read this as 3, like we're not excited that we have a 3, and that's why we've got the exclamation mark there. That notation just tells us how we're going to create our answer from the number 3. So that in general, if I've got a whole number and I see the exclamation mark beside it, it tells us start at that number and multiply all the numbers from that number all the way down to 1. And these numbers are very useful in counting different ways of arranging things. So if we go back to our picture problem, imagine that a 4th friend, Emmy, pops by, and we want to look at all the different ways that we can line up the 4 friends. Now, there's going to be a lot more ways. We could list this out, but it's starting to get a little bit tedious. But if we go through the same analysis that we did before, we see that there's 4 possible choices for the first person. And for each of those 4 choices, there's going to be 3 possible choices for the second person. So if Emmy's first, I can either have Lenny or Sophie or Srin as my next. And similarly for each of the other choices. Down the line, for each of those choices, I've got 2 possible choices for the next person, and now I've used up everybody but 1, so I've got 1 possible choice for the last person. So our total is just going to be 4 times 3 times 2 times 1, and we've seen already that this is just the definition of 4 factorial, or 24. The values of these factorials grow very quickly. Let's take a look at the growth of the factorial for some small values of n. We'll define 1 factorial as 1. Then 2 factorial will be 2 times 1, which turns out to be 2 times 1 factorial, which is 2. 3 factorial is 3 times 2 times 1, which is 3 times 2 factorial, which is 6. We're kind of running out of space, so let's make things a little smaller. 4 factorial is going to be 24, 4 times 3 factorial. 5 factorial is 5 times 4 factorial, or 120. And we're really quickly running out of space. And even if I shrink things down, we're going to run out of space quickly. So let's just look at the numbers for the next few. 6 factorial turns out to be 720. 7 factorial turns out to be 5,040. 8 factorial is 40,320. 9 factorial is 362,880. And 10 factorial is 3,628,800. What that means is if you had 9 friends and you wanted to line the 10 of you up to take pictures, there's over 3 million different ways that you could line yourselves up. Now, when I was teaching factorials to my senior high school students, a lot of times I'd read them this children's book called Anno's Mysterious Multiplying Jar. This is a cute little story that shows factorials in motion by looking at an island that has 2 hills, and on each hill there's 3 villages, and so on down the line to show the factorials. At the end of the book, they go through and tell the story again, but they use a single dot to keep track of the size of the factorials. And when they get up to 7 factorial, they fill 2 pages with dots. And they explain that they can't do it anymore because by the time they get to 10 factorial, they'd have to fill a number of books of this size just with dots to be able to show it. So let's look at a couple of situations where these factorials show up, where we'll take an idea and get an idea of how big these numbers can actually get. Okay, suppose we're in school and we have a class with 28 students and 28 desks. We want to know how many different ways that we can arrange the 28 students into the 28 desks. So we know that there's going to be 28 ways to place the first student in the first desk and so on down the line, and that's just going to be our definition of a factorial. And when we calculate this, we get 304 octillion and then some. I calculated this using Wolfram Alpha online. I'll leave a link in the description of this video. So this is a huge number. So let's try to get a sense of how big this number is by picking something small. So suppose we had that number, 28 factorial drops of water. How much is that? Take a second and think to yourself. Pause the video. how much water would you have if you had that many drops? Would it be enough to fill a tub? Do you think it'd be enough to fill a swimming pool? Or would it even be enough to fill a lake? Take a second and think about it, and then come back and look at our analysis. Okay, to get a sense of how much this is, we have to turn this into something that we can visualize and work with. So I looked up on the internet, and a drop of water is about 0.05 milliliters, if we're looking at it in a medical sense. So that's what I'm going to use. So if I multiply by 0.05, my 304 octillion comes down to 15 octillion milliliters. Milliliters, again, is still pretty small. So let's convert that to liters. There's 1/1000th of a liter per milliliter. So that becomes 15 septillion liters, still a lot. We could probably get a sense that it's going to be too big for the tub, but the other ones, it's going to still be hard to judge. So let's convert this into another measurement that we can use, which is cubic meters. And 1 liter is 1/1000th of a cubic meter. So I get 15 hextillion cubic meters. Now, if I look at a tub, maybe a tub is a little bit more than a meter long, a little bit less than a meter wide, a little bit less than a meter high. So its volume is going to be around 1 cubic meter, give or take a bit. We can tell that this number is way too big. So there's going to be way more water than will fill a tub. What about a pool? Well, a pool's length might be 10 or 15 meters. Its width might be 10 meters. Depth, a couple of meters. So a couple of hundred cubic meters seems like a reasonable volume for a pool. Again, that's way bigger than that. So that one's out of the race. For a lake, it's a little bit harder because we can have lakes that are kilometers and kilometers long. So maybe we need to convert this into another measurement. So from cubic meters, let's convert it to cubic kilometers. And 1 meter is 1,000th of a kilometer. So a cubic meter is going to be 1,000th cubed of a cubic kilometer. So when we put all that together, we get the more reasonable 15 trillion cubic kilometers. And if we look at a lake, like even a large lake might be 20 kilometers long, 10 kilometers wide, not a kilometer deep, but if we look at that, 200 cubic kilometers might be a reasonable estimate for a biggish sized lake. Maybe the Great Lakes are larger than that. But if we compare this number to the number we're dealing with, chances are even the Great Lakes aren't going to be big enough to deal with that. And if you check out the Great Lakes, Lake Superior is around 12,000 cubic kilometers in volume. So that's out of the race. So let's look at this a different way. What if we put all of that water into a big ball? How big is that ball going to be? So we know the volume of a sphere is 4/3 pi r cubed. We set that equal to our 15 trillion cubic kilometers. We divide through by the 4/3 pi, and we end up with about a little bit over 3 trillion cubic kilometers. We take the cube root of that, and we get a reasonable 15,000 kilometers. So we would have a ball of water with radius 15,000 kilometers. Now that's pretty big. So what's something else that's really big that might compare to it? How about planet Earth? Planet Earth has a radius of about 6,000 kilometers. So our ball next to the Earth would look kind of like that. What that means is if the Earth was totally made of water, our ball would have more water in it. And in actuality, if Mercury, Venus, Earth, the Moon, Mars, and its moons were all made of water, we'd still have more water in our ball of water. So that just shows you that 28 people, which is a normal size for a class, the number of ways to arrange those people is huge. It's sort of mind-numbingly large that it's hard to picture how big that is. Let's look at one more problem dealing with an everyday thing that leads to a large number, and then try to put our heads around that number. So we want to figure out how many different arrangements there are of a standard deck of cards. So there's 52 cards in a deck. So we saw that if we want to arrange 52 things, that's going to be 52 factorial. And that number turns out to be this number here, which is pretty big. If I pronounce this correctly, this is 80 unventillion and a bit. This is an unimaginably huge number. And this is the number of different ways that a deck of cards can be arranged. So let's try to put that into some perspective. So let's do it this way. Let's imagine that every person in the world was given a deck of cards. And every second they are able to shuffle it into a new arrangement that has never been seen by any of the other people. How long would it take everybody in the world doing this together to cover every possible arrangement of the cards? So again, if you want, take a second, pause the video, and think about this. Think in terms of roughly what you think this is, and just go for a guess. Now, I'm going to spare you with all the computations of this. It turns out that for people, if all 8 billion people roughly in the world did one arrangement a second each, it would take 300 duodecillion eons to do that. And an eon is 1 billion years. So just to give a little bit of perspective on that, the universe is thought to be around 14 or 15 eons old. So that's 1-4 with no zeros. This is significantly larger than that. What this means is we could never, in the history of the universe, go through all of the possible arrangements of the deck of cards. And what that means is, if you pick up a deck of cards at your house and it isn't brand new, it's been shuffled a bunch of times, if you give it a shuffle or two, there's a really good chance that the order that it's in now is an order that nobody in history has ever seen before. And there's a good chance that nobody in history will ever see it again. There's just that many arrangements. It's crazy. So you might think, hey, people are slow. What about computers? All right. So let's suppose that we replace our 8 billion people with 8 billion of the fastest supercomputers. And we'll assume that these computers work at a rate that when we're measuring the speed of a computer, we talk about how many operations it can do a second. And we'll assume, just to make things simple, that each one of those operations, they're able to make a new arrangement of a deck. They can't. They would need many operations to do that. But just to make things simple, how long do you think it would take the supercomputers to do it? take a second, and let's take a look. Now, it's only going to take 600 sextillion eons. So even the computers aren't fast enough to be able to do all of the arrangements of a deck of cards. And 52 isn't that many things. So we can see how in mathematics, yes, computers can help us, and computers can help doing computations of things. Computers can do what they're told very, very quickly. But we can't just sort of have computers mindlessly doing things. Because in some cases, the problems can get so big that the computers aren't fast enough to do it. We still need people to think about problems, think about some shortcuts that we can do to help the computers get there quicker. So factorials are used all the time in mathematics. We've seen that they are used in counting. We've used them specifically for the number of ways of arranging a number of objects where we're arranging all of them. That's not always what we have to do. For instance, in Canada, we have something called Lot of 649, and I know around the world there's probably a lot of very similar lotteries. This is a thing where you can buy a ticket. You choose 6 numbers out of the numbers 1 to 49, and that becomes your ticket. Now, the order that you pick the numbers doesn't matter. It just matters what numbers you pick. And we can use the factorials to help us figure that out. Now, it turns out that the total number of tickets is given by 49 factorial over 6 factorial times 43 factorial. We won't talk about that now. Probably in a future episode, we'll talk more about these types of things. But just to give you an idea, that turns out to be about 13.9 million different tickets. So if you buy a ticket, your chances are about 1 in almost 14 million of winning. Not very likely. Another place, as I've sort of alluded to, is in probability theory. Probability, sort of the very definition of probability is the number of ways that something can happen over the number of total possible outcomes of our experiment or thing that we're doing. So these factorials can come in handy for calculating those as well. So if we're doing something like poker and we want to know what are the chances of being dealt a royal flush and hearts at poker, what that means is if I took a shuffled deck and I dealt you 5 cards, what are the chances that the 5 cards are the ace of hearts, king of hearts, queen of hearts, jack of hearts, 10 of hearts, in some order. They don't have to be in that specific order. And again, we can use factorials to figure that out. Our answer is 5 factorial over 47 factorial times 47 factorial over 52 factorial, which is 1 in about 2.5 million, or about 0.00004%, or not very likely. So you'll see the form of this is very similar to the form of the other one. And again, we'll return to this at a future episode. Before we end, just a couple of websites that I use to help do this video. The first one is Wolfram Alpha, which is a wonderful online computational tool. You can type in your factorials and it'll actually calculate it to all of the decimal places that you want and tell you various things about it mathematically, as well as doing a number of other things. If you haven't explored Wolfram Alpha, I highly suggest that you do. Another one is the MacTutor History of Mathematics. In the history, you'll find all kinds of biographies of mathematicians. For instance, one of my favorite is Leonhard Euler. You'll get a nice history on Euler, talking about his work and so on, as well as seeing a whole bunch of different pictures of him. Some of them might even look a little bit familiar. As well, on the site, you also have a bunch of famous mathematical curves, such as the cardioid, where it shows you this interesting type of curve, gives it its equations, as well as a description. And another nice thing is this mathematician of the day, where if you click on it, and today's March 22nd, 2022, if you go, it'll show you all the mathematicians that were born that day, all the ones that died that day, as well as a quotation and various other things. I'll leave links to both of these sites in the description of the video. So that's it for this edition of Math Shorts. I hope you enjoyed looking at factorials. Come back and check us out in about a month, and there'll be another episode up on some mathematical topic. Until then, keep counting